Good afternoon, everybody. I'm here to present this seminar that I was invited to give from the StoRIES Association and project. As you see, my name is Massimo Guarneri, and I work in the University of Padua. Since several years, I am engaged in flow battery, and particularly in scaling up flow batteries toward industrial applications. So my talk will actually focus on flow batteries rather than open batteries. That is quite a wider concept, but actually I'm not an expert of other types. Okay, let's go on. So first of all, I think it is important to understand why we study and design batteries, stationary batteries, and particularly flow batteries, which service we aim to provide with these technologies. And the services are services that are required by the grid, generally speaking, and we can distinguish the support that energy storage can give to renewable sources, which are intermittent by nature. The most important of them, at least, like PV and wind. And as they penetrate into the share of generation from the sources increases, more and more energy storage might be provided to compensate their intermittency. And so this is a scheme that indicates how this grid will work. They have renewable sources assisted by storage. But this is not the only service that we can provide to the grid. There is another important field of application, which is a smart grid, which means the evolution, a natural evolution of grid toward more intelligent, more smart, more efficient, and more performing grids, which are going to be implemented and to expand in the future, even supported by artificial intelligence. And to put together this concept, we can distinguish a number of different services that storage can provide to this kind of applications. And here I listed some. We can differentiate these services based on the time of intervention. Let's say now intervention. I will go into more detail later on. And fast storage modes qualify what is intended as power quality. We can distinguish some of the services I list here: user power quality, grid stabilization, frequency regulation, which is also primary regulation for the grid, voltage sag compensation, power smoothing, and even we can put here UPS, which is intended to provide continuity of supply in case of blackout and so on. And then there are the slow storage modes, which are more intended for energy management. And there are again a number of different concepts, often I must say overlapping, but every name here indicates a specific feature of the service to be provided: time shifting, load shifting, energy arbitrage, peak shaving, load leveling, load following, power balancing, load factor improvement, and even black start, which means the capability of a grid to start to power on alone after a blackout, LDES, which means long duration energy storage, which is a concept that is expanding and becoming more and more important in this time, and even investment deferral. All these services involve the operation of longer times. And here I want to go in detail somewhat into the long duration energy storage concept. providing you some idea taken from recent literature. This is a diagram that shows that if we want to increase the penetration of the renewable up to 100%, which means we totally decarbonize the grid, we give up with coal, oil, and so on power station, we need to have extremely long duration. This is in hours of the storage. Actually, this storage duration is the discharge time at rated power. Now we typically, the system, we think about, at least when we consider batteries, which is of interest for StoRIES, we are down here in few hours. But you see that the full penetration of renewable will need much, much longer duration time in the scale of day, weeks, and even season. And in order to implement this condition, it will be required to expand a lot the long duration energy system that now we are about here in this moment, are almost negligible compared to other technology. Lithium-ion batteries are expanding strongly in this period. They will go on expanding, but they will not cover the long duration energy storage that will call for other different technology you see here. And so at this moment, we must consider that actually we have a number of different services to provide, as I sketched in the previous slide. And we can do this with different technologies that are available to provide energy storage. This is a schematic, which is also dated. I must confess, I had no time to update to recent year, but this is just to give you an idea that we go from pumped hydro energy storage, which means hydro storage in water reservoir in pumping station, which can provide very high power and very long durations. But we have on the other side super cap. We stay down here with the very fast services and low power. And in the middle are a number of different technologies, from flywheel energy storage to thermal energy storage and so on. What is interesting here is that you see this dotted line, blue dotted lines, this envelops all technologies where electrochemistry is used, which means lithium-ion. I'm sorry, I must confess that the area covered here by lithium-ion is much smaller than the actual rating of present systems, which have expanded a lot. Lead acid and so on, and the sodium sulfur and so on, and also the flow battery and hydrogen. I put also this inside this as a kind of chemical energy storage. And so they become to be extremely strategic because they are able to cover a very wide part of the full diagram. That given, I must also come to detail better what is the time that is presented here. This involves the response time, how fast the system responds to the call for power delivery, and the duration time. The duration time is the discharge time also, which means how long the system can discharge power at rated power, can discharge at rated power. And these are not the only two times actually that are involved in designing energy storage system. There are a number of other timing that we have to consider. So the response time I already introduced, depending on the technology, it goes from some hundreds of microseconds to tens of minutes. But we have also the discharge time already introduced as well. It goes, as you can see, from tens of seconds to thousands of hours, and several thousand in some cases, I must also say. But we have also the storage time, which means how long we can store energy inside the system without self-discharge. Here, the parameters that is involved in the self-discharge rate, and this also can vary a lot depending on the system. Then we have also to consider the cycle life. It means how many cycles of charge and discharge the system can stand before being going out of service. And here again, the rates can be extremely large, from few hundred of cycles to several thousand of cycles. Then we have the calendar life, which means how long it can exist before becoming too old by itself, independently of the service it provides. And even here we have extremely long, extremely wide range of duration. So all these 5 times must be considered when qualifying the time performance of a storage system. To give you an idea, we are focusing on electrochemical systems here. So I give you an idea of the 2 present records. In this moment, the largest lithium-ion battery existing in the world is rated almost 1,000 megawatt of power and more than 3,000 megawatt hour of energy with the duration of 3.5 hours. You can see this is in California, and the largest flow battery system in operation. This is a very recent communication from China. It is the battery rated 175 megawatt of power and 700 megawatt hour of energy, which means a discharge duration of 4 hours, which is in China, as I said. And so the system are already expanding toward these big sites, long duration energy service, as I was telling you before. But we can see this even better in this diagram, which shows what is happening in the last 8 years. This is the average discharge duration of battery systems that have been installed during the years. And as you can see, about 8 years ago, 9 years ago now, it was in the order of 1 hour, the average discharge duration, but over the year it has been increasing quite significantly, and now the average is close to this moment even above 4 hours, I can say. And this evolution is also considered in some analysis provided by involved association. One is Vanitec for vanadium. This analysis actually applies to vanadium redox flow batteries, but it can be considered basically valid also for other kind of technology. And see the expected expansion in next year for this kind of technology in different areas around the world. This is also confirmed by a recent report of the Department of Energy in the United States that considered how long duration energy storage can be achieved. And it indicates that actually flow batteries are in the forefront of the technology for giving these services in the next years, the next decades. So now I go into flow batteries, as I promised, and I recall quickly the architecture for those of you that are not familiar to the concept. It involves cells that are formed by 2 porous electrodes. They are porous because they are going to be soaked with the liquid electrolyte, which is actually the energy storage part of the system, and which undergoes the reaction to charge and discharge energy. The 2 electrodes are separated by a membrane, typically a polymeric membrane, as you can see sketched in the picture on the right. And there are 2 basic configurations at design level for putting together these things. The flow-through design, which means that the porous electrode is directly flowed from one side to the other with the electrolyte, or the liquid electrolyte, and the flow-by configuration, which actually means that the the electrolyte flows on the side of the surface of the electrodes, and from here it permeates into the electrodes. This makes a quite important difference at design level and performance level between the possibility offered to the designer. All these cells have to be put one after the other into a pile, a stack, and actually stack is the word that is used, and so as to allow electrolyte to flow in the whole system. If you work on with the lithium-ion battery, you need to pack immediately them one after the other. Usually we leave some room between one cell and the other, at least for cooling reasons. Here it is different. Here every cell is put all together in a stack to allow efficient circulation of the liquid electrolyte, basically. And so the system, typically the converter, the stack, appears a shape like this. And with the cells which are connected in series from an electrical point of view, but are connected in parallel from a fluid dynamic point of view. And the size of the stack defines the power of the system, while the energy is defined by the volume of the electrolyte which are stored in external tanks. But this is not all you need to make the system to work properly. You must interconnect the tank with the stack. So you need the balance of plant, piping, pumps, and so on, casing, safety system, and so on. Then a system for connecting electrically the battery to the grid is needed, what is called the power connection system, which controls the electrical flow bidirectionally when you charge and or discharge the battery. Then there is the flow battery management system, which has a similar function to the battery management system in lithium-ion batteries, but it's actually more complicated because it has to manage with the different physical variables. So it is a multivariable controller typically, and then there are a number of other ancillaries that must be added, which means that in order to have a flow battery really operating, you do not need just a battery. You need actually a real engineering system composed of all this stuff. Otherwise, you have also component of a battery. So in this moment, the research ongoing on flow batteries is quite wide from the low TRL. There are even more than 50 different types of flow battery described in the literature, differing one from the other for the chemistry used, and possibly there are even more. Some of them are neither yet described in the literature, and the main distinction that is done actually, as I said, on the type of electrolyte, of the chemistry used, and there are two major types. We can distinguish the metal flow battery, typically at high technological readiness level. Some of them are mature or very close to mature. Some of them are already marketed, even in very large sizes. I mentioned the big system that went into operation recently in China. First of all, the vanadium flow battery, but there are also the zinc bromide, zinc iron, hydrogen bromide, iron. Some one of them, I must say, with the pilot system that are going to be put into service in the next future, but on the large scale in any case. The problem of vanadium I mentioned here is that it is very good performing, but unfortunately costly, and in European Union it is classified as a critical raw material, which means, which is the reason behind the search for between the search for alternative chemistries. And then there are other family, a very large family of other chemistries, typically metal and organic, at low technological readiness level. They are typically studied on the very small sites. Some larger pilots have been also produced, but only at a pilot level. And here again, I can mention the oil copper, the polysulfate bromine, iron chromine, and so on, and particularly the organic compounds, quinone, halogens, and polymers that are being studied in several chemistry laboratories. And even fluorolithium ion is an emerging concept. So there is a wide range of different options to follow in the next year and to understand what will be the most promising, but also the winning sooner after. A different classification that we can do on flow batteries is based on pure and hybrid flow batteries. Pure flow batteries mean that they use liquid electrolyte on both sides, on both electrodes, on both polarity, while the hybrid flow batteries use deposition on one of the electrodes and fluid electrolyte on the other side. And another distinction is between aqueous and non-aqueous flow battery, depending on the solvent that is needed in the electrolytes. So typical characteristics are the scalability, which means that you can increase to very high level of power and energy, as mentioned, from few kilowatt to several hundred megawatt of power, and similarly for the energy. So they can fit also different power and energy demand without needing a huge number of components in order to achieve extremely high power and energy with lithium ion that people need to put together an extremely huge number of single cells, and increasing the number of cells increases intrinsically the risk for hazards, while having a smaller number of components, which is in the nature of flow batteries, reduces these risks. Then they give fast response, at least if they have they are kept in standby mode, but they can also allow for very long storage time, even several weeks, if they are set in the no self discharge, in the off mode, which means no self discharge. Then, at least for pure flow batteries, which are using liquid electrolyte on both sides, that they have a free, total independent energy and power rating, which means that they allow for very long discharge time as well. Typically, these plants are up to now have been produced from 4 to 10 hours of discharge duration, but actually they can fit every other duration quite naturally. And to go on with other typical features, we say that some of these flow batteries, at least those based on the same kind of chemistry on the both electrodes, do not suffer from cross-contamination effect, which means that they can stand for very long life duration, cycle life duration, and candela life duration, because they do not go some fast aging of internal components like electrodes and membranes, which impact immediately on some economic figure that we will meet later in this presentation, particularly the levelized cost of storage, making it close already now to the target posed by federal organizations like the Department of Energy or Horizon Europe in this continent. Aqueous flow battery has also a very limited hazard risk. They do not undergo the risk for internal fire or explosion, and they have also negligible environmental impact and very favorable life cycle assessment. And typically, they do not use precious catalysts, differently from hydrogen energy storage system that need at this moment for precious catalyst in electrolyzer and fuel cells. And going on with the typical feature, they present typically high level of recyclability and circularity because most of the material can be recycled or recovered for further use. Some flow batteries can be the electroactive materials, I'm speaking about vanadium specifically, can be recovered and recycled because they do not go any cross-contamination, as I mentioned before. On the other hand, there are also some issues, of course, naturally. Vanadium has the problem of post and CRM classification, as I was saying. And this is the reason why, as I mentioned, a strong and wide search for other chemistries is ongoing, not only in Europe, I must say. And also other issues comes from the use of some particular material. I mentioned in particular PFS that in this moment are under the threat of ban from the European Commission, and they are used in membrane, in gasket, in sealing. This called from the finding of alternative materials. And now I go directly into all vanadium flow batteries. And the reason why it calls all vanadium is that thanks to the capability of vanadium to exist in different states of ionization, they use two-state of ionization, what is called vanadium 2 and vanadium 3 on the negative side, and what is called vanadium 4 and vanadium 5 on the positive side. And the 3 and 4 actually correspond to the discharge condition, while 2 and 5 correspond to the charge condition. So during charge, vanadium 3 convert to 2, vanadium 4 convert to 5, and conversely during discharge. And while disappear now, okay. So these are the reactions that occur during charge and discharge, as I was mentioning now, and that given what is the performance of the single cells, the theoretical open circuit voltage at 50% of state of charge is 1.26 volt. This comes out from Nernst equation, but actually the experimental value is a little higher because the Donan effect has a beneficial contribution increasing the open circuit voltage. And actually this voltage is not very stable during charge and discharge. It can range by 0.6 volts depending on the condition from fully charged to fully discharged. The typical current density that the cell can stand in this moment are in the order on 150 milliamp per square centimeter, and overcharging is a characteristic of this system. They can stand 4 times more for a limited period of time. And when going to scaling up the system to industrial level, we need a large active area in the cell, which allow for the same current density to achieve higher current, and then to put several cells in series inside the stack to increase the voltage. And so having high powers mean to have a large area and long series in the stack, so as to have higher power. Exactly. And to scale up the energy, instead, we must use large tanks where there are also some issues, which are issues connected to the mixing of the solution when during charge and discharge, which is a problem actually that is emerging in the last years, and it has been longly overlooked in the past. And how to work in this direction, I mean in the engineering view, in scaling up the system. This is what we are doing in our lab in Padova. We work on a real industrial level system. This is rated 10 kilowatt in power and almost 30 kilowatt hour in energy. And this is a complete system, as you can see, with big tanks, big stack, and all the ancillaries that were mentioning before. Sorry, what is this? Here, yes. So you can see the power conditioning system, the flow battery management system, and then all the equipment, all the sensors, the transducers that are needed to develop the experimentation at the scientific level on a system like this. These are the kind of performance that we have achieved. They are also a little dated, but just to give you an idea, we can consider the reference at least for present system. So you see typically current density in the order of 150, in this case 200 amps, quite far from overcharging to operate properly, but depending on the state of charge. And these are kind of analysis that are needed to qualify the steady state of operation of the system. But we must also investigate the system in the fast mode. And in this case, we use electrochemical impedance spectroscopy to qualify the internal impedance of the system and how it differs from cell to cells, from depending on the state of charge, on the load condition, and so on. But actually, this is also not a complete view of what the system can do in terms of fast response. So we investigate these issues also not in the frequency time, which is what the impedance spectroscopy does, but actually in the time domain, and to see the time response in real condition. And these are properly the operation at the moment of this kind of system. Of course, the question now is to develop this system toward a future more competitive system. Actually, we up to now work on flow battery based on vanadium because they give very good performance. But since the evolution of this kind of this family of energy storage system can be also in other direction. I mentioned the many chemistry that are under investigation. Some other can emerge as more competitive in some years than vanadium. This is possible. And this calls for engineers to investigate on the general term what can be the technology to put in the system to make it operate also with other chemistries. And in this way, the concept of the universal flow battery is emerging, not only in our lab, also in other laboratories, to have the technology ready soon for emerging chemistry as soon as they can. Now, the problem for the future is exactly this. Will flow battery have a future in electrical grid? This is the question, which actually means something. I go into more detail in this question. I pose now the problem in a different way. Will they gain market profitability and competition beyond regulatory propping? Which means, yes, regulation can impose some kind of technologies and they can be forced to be used. And this could happen also with flow batteries. But this has to be thought as, for instance, the national health system, which asks also for money to provide the service, or is something different. I mean, this can be a technology that can go on the market and be profitable, and also in comparison with our technologies. This is a more challenging question, of course, because if the technology is protected by regulation and laws, it can stay quiet like exactly the national system. But being competitive means to have the possibility to go out of the boundary of a nation, of the continent, conquer also other markets. To understand this, to try to understand this, we developed a techno-economic analysis, which requires the construction of a special model that takes into account the technical and the economic factors. The economic key performance indicator that we must consider are the capital expenditure and the operational expenditure. These are total cost figures. It's better to refer them to the energy rating. And so you have the unit capital cost and the unit operating cost. And what comes inside the capital cost and the operating cost? Of course, the capital cost, the capital expenditure means the cost for the power components, the cost for the energy components, the cost for the balance of plant, all these devices that we added, and also the cost for the end of life. While in the operating expenditure, which means how much we spend yearly for operating and also for maintaining the system, maintenance cost, efficiency, which impacts of the operating cost, and the duration in terms of cycle life and calendar life. So how many years we can use the system to spread the capital expenditure over this year. And then we have also to take into account economic and financial factors like the discount rate and the prices for electricity. Every time we buy it for storing, and every time we sell it for selling, for discharge, during discharge. But actually, it is not easy to put together all these figures. They have different point of view, different reference. So we need some synthetic key performance indicator to put everything together. And these synthetic indicators that we choose where are the levelized cost of storage, or also you can call levelized cost of energy. They are quite similar actually, and the net present values that combine in a single value the whole performance of the system. And to put this together, we had to manage a quite complicated model, which is synthesized in this flowchart. You see the different factors considering, for instance, assembly cost, labor cost, power cost, and so on, that go into the capital investment. And here below, mixing process, generation processing, maintenance, that go into the maintenance cost, the OPEX, and all together, put together to create the levelized cost of storage and net present value. So now we need to start to assemble the model. And the first point, the first step is the unit capital cost. The unit capital cost is the capital expenditure divided by the stored energy. The capital expenditure, as I said before, is then composed by the, what is this? Sorry, here it is. The power cost, the energy cost, the balance of plant cost, and the assembly cost, all divided by the rated energy. The levelized cost of storage at the moment is composed in this way. Now you see the model to be used. While the net present value is composed in this way. We have a number of different parameters that are involved, and these are the parameters, which means the yearly discount rate, the round-trip efficiency of the system. You see that appears here. The discount rate instead appears here, here, and so on. Sorry. The year index, how many years we are going. It's a very sensitive mouse today, mine. Then the electricity purchase price and electricity sales price are also involved, as you can see. And we must start constructing this equation, but how do we compute the capital cost? How do we compute the capital power cost, the capital energy cost, and so on? So we must go develop further the model, and this is what we are doing. Here is the model used to build up the power cost, which means the cost of a stack multiplied by the number of stacks. Because if the power is small, 10 kilowatt, even 30 kilowatt, you can build up the system with a single stack. But if you need instead 100 kilowatt, you cannot use one single stack. You must use many stacks, each rated, for instance, 10 kilowatts. So 10 of them. And if the system is rated 100 kilowatt, it goes on like this and so on. And so the power rating of the stack can be figured as with this expression, where we have the open circuit voltage less the voltage drop during operation. J is the current density. ASR is the area specific resistance of the system. This goes multiplied by the current, which means the current density multiplied by the active area and multiplied by the number of cells inside the stack. So this is the power rating expressed in terms of basic operating parameter, OCV, ASR, and J, and the sizing parameters of the stack, the area, active area, and the number of cells. Here is a typical expression for the open circuit voltage in the system, the next equation actually. And then once we have defined in this way the area, the active area, and the number of cells, we are ready to put together the cost of the material involved in the stack, which is given by this expression. Now, I explain you the different parameters appearing here. They will appear soon on the right side. And the energy cost goes similarly, takes into account the cost of the electrolyte, the cost of the tanks, and so the cost of the volume of electrolyte contained into the tanks, and the cost of the tanks with typical figures are reported here. Here again, we need to have the definition of the volume. It depends on the energy to be stored and other parameters of the electrolyte, the molar concentration, and so on, the Faraday constant, and so on, and the variation of state of charge from fully charged to fully discharged, which is not 100%, of course, and so on. The average open circuit voltage during operation. And these are all the parameters. I show you them all together here in this table that are needed inside all this equation. So you see, for the cost of the material in the stack, we need to have the cost of the cell component, membranes, bipolar plates, electrodes, gasket, flow frame, and so on. The cost of the stack head and current collector, to only for any stack. The number of cells in the active area, which are the sizing coming out of this equation. The current density, of course, which is the standard performance parameter I presented before. And so we have finally the power of the stack, and so on, and so on. The number of electron transfer, which is quite easy for vanadium, it is 1. The vanadium volume, the vanadium molar concentration, the cost of the electrolyte, of the vanadium electrolyte in this case, the tank volume increase, which is, of course, a free space to be left to operate the tank while charging and discharging, circulating actually, the electrolyte in the tank, and the cost of the tank for unit volume, and so on. It is not all, because these are only the two main expenditure figure capital expenditure figure, but we have also other, as I mentioned, the balance of plant. We must take into account the battery management system, the power conditioning system, the cost for the electrical circuit, the circuitry that must be added to the system, the cost for the hydraulic system, and typically we use a unit cost referred to the power of the stack that must be multiplied by the power at the end. The assembly cost, standard figure in this case is 10% for a semi-manual assembly. And as regard the cost of the battery management system, we did not use a linear equation like this. This is linear, of course, in terms of power, but rather a less than linear equation. It is an exponential dependence on this factor here. And then we had also to account for the operating and maintenance cost during exercise, which means the cost for regenerating the system and during some process of, say, degradation that requires some action to be compensated during operation. There are two kinds of operation actually to be implemented. One is easy remixing that can be done quite easily in every system, but actually it involves a loss of a charge anytime you operate it. And the regeneration system, where it is quite an occasional or exceptional operation to be implemented in case some side effect occur into the electrolyte. And again, we go into the unit operating cost in this way, year after year. Here are the cost involved, and these are, sorry, this is also for this actually, sorry. The financial parameter, again, that we have to take into account are basically the most important is the discount rate that the investment is paying for being financed. And we used here a model that is called the capital asset pricing model. Provided by economists, of course. It takes into account the free risk discount rate, which means the discount of public bond, national bond that involve no risk. If we want that someone give us money, we must be ready to pay a discount rate higher than this. That is basically the mask risk premium, the increment multiplied by this coefficient that depend of the kind of investment, the kind of technology and so on. The more risky is the technology, the higher is this beta parameter. And how we compute this increasing factor in the risk of the investment. This is actually computable from balancing report of the companies. We found some major company working on flow battery around the world, in UK and the United States, in Japan, in Canada, in China, and Europe. A, B, C, D, and D are real case. I don't mention here which are the company. It is not difficult to understand, but I remain on the confidential side. And you see that the beta be computed here to put into this equation. So at this point, we have a quite complex model finally, and we must only populate with the numerical value all of these parameters that are needed in the full model. These are the technical parameters that we use in the beginning, which are in line with present performance of flow batteries. These are parameter related, the corresponding cost of the parameters involved. So the cost for membranes, for electrodes, for bipolar plates, for flow frame, gasket, and so on. You see all the different components, including also the tanks and the electrolyte. Then we have the prices for the balance of plant, which I repeat are the power conditioning system, the electronic converter, the electric system, the piping, the pump for circulating the power, which is less than linear equation, and the battery management system and manufacturing, as I mentioned already, 10%, and then the other economical cost, market economic cost, market parameter, which are the unit cost for generation, the price for selling electricity, the price for purchasing electricity, the discount rate coming out from the previous model, which is almost double in this moment than the discount rate we used making this accounting, this computation, and the vanadium value at the end of life, which was assumed to be 0, which is a little quite surprising. We'll come back a little later on this point. It is always said that the vanadium does not contaminate. It can be totally recovered, and it constitutes an asset, not a necessary cost in this way. But actually, if you go in this moment to try to sell vanadium on the market, you do not find anybody ready to buy. The market for recirculating vanadium is not yet started. So we had to put a 0 value in this position. Okay, putting all together, these are the result of the computations. You see that here in this diagram, we have two figures of cost. One is the unit capital cost, investment cost. In the case of 2 hours of discharge duration, 4 hours, 6 hours, 8, 10 hours, which means the ratio between the rated energy and the rated power. And you see clearly that as longer is the duration, as lower is the capital cost, unit capital cost, which is expected, of course, but actually it is in the order of 300 euro per kilowatt hour. It is not the selling cost for a company that put on the market the battery, but the cost for the company itself to produce the battery. Remember this. And this dotted lines is the levelized cost of storage. You read the values here, and you see the levelized cost of storage in this moment for a very large, for a long duration system, 10 hours, which is the top performance now in this for this system. It is in the order of 0.28 euro for kilowatt hour for cycle, which is it good? Is it bad? Possibly it is already good, of course, if we need to make a technology available to respond to a regulation requirement under state protection, let's say economical protection. But we should remember you that the idea was to check if this is profitable. And to understand this, I will use the net present values. The result is this. You see in the abscissa down here, the unit capital cost from 1000 to 1000, 1000 to 1000, we are in this range. And you see what happens. The area of the diagram is green here and is red here. It means that only if the net capital cost would be, the unit capital cost, sorry, less than 100, we could be profitable. We could invest here earning money in operating the system. But 100 euro per kilowatt hour is here. No one of the systems reaches this level. They are too costly actually. And so the actual system that we have here for a duration of 5 to 10 hours are not profitable, even less if the duration is shorter. And this is, I remember, with this discount rate in the order of 10%. So at this moment, we should conclude that it's not wise to invest in this technology. But this is not the topic of my investigation, the aim of my investigation. The aim is what can happen in the next year. Is the situation going to remain the same or is going to evolve? And what is the research and development path at we start looking at the low technological readiness level, which means investigating on electrolytes. Electrolytes have some issues, we have seen. They require big volume and they are costly. Why? What are the key factors that affect these issues? The energy density, which is quite low, the price, which is quite high. I'm referring to vanadium in this moment, of course, and the aging rate if we use different electrolyte. So what can we do for improve these issues to modify this key factor? We can go into looking for some kind of physical chemistry of the electrolyte that increases the concentration, which can be done with micro nano particles of vanadium in suspension. We can use additive capable of stabilizing vanadium also if it is produced at a lower level of purity, and in this way, in a cheaper way. We can use alternative chemistry, of course. I said several times this. Basically, important are the chemistry based on iron that are becoming more and more popular in this moment. Other chemistry, such as vanadium oxygen, that are in a phase of exploration. And we can also try to extend the capacity exploitation, to expand the range of SOC that we can work. In the previous slide, you could see that we assume an 80% from 10% of charge to 90% of charge from totally discharged to totally charged. If we are able to expand this, we achieve a better exploitation of the electrolyte, and so we reduce the volume for the same energy exchange. And can we do this? Yes, based on a number of literature, there are very promising results going in this direction. Here I mentioned some of them, and looking into what has been obtained at basic investigation, low technological readiness levels, it is possible that the electrolyte energy density rises to 84 watt per liter from 28 it is now, and even in some report here indicated to much more, 149 watt per liter, which is a dramatic increase in energy density, which means also a reduction in cost and so on. Oh, by the way, the literature in this case is quite vast, and I had no space to report all of them, so I don't want to be exclusive for other. I apologize for some contribution that someone of the attendee can consider important as being omitted here. And it's the same for the next slide that we are going to see next. So now we go into membranes. Even here we have a number of issues. The voltage losses, which mean the ohmic over voltage, the ion migration, which means spaces over crossover, which should not happen, but actually happen, the ionic current, the durability, the environmental compatibility, and so on. And here the parameters that quantify this factor as the conductivity, ion conductivity, which affect the area-specific resistance for what refers the membrane, the permeability, of course, to ion, electroactive ion, the current density, the durability, the aging rate, regulation compliance, and so on. And so the pathway to improve are increasing selectivity, reducing crossover, and by different technology that also here have been reported. We must look to comply with the regulation, particularly regarding the use of FAS, and different solutions can be found in ion electron membrane and exchange membrane and cation exchange membrane. Here again, there are many reports in the literature referring on the very positive result already found, and here some of them have been reported. I reported, again, not all, of course, and putting all together, we can expect that the permeability of the spaces will increase dramatically, reducing the resistance. At the same time, the losses, which means crossover effect, can reduce quite strongly. And also the current density, it goes together with the permeability. These parameters can increase quite strongly, while at the same time there are studies going into the direction of avoiding the use of fluorine components in the membranes. In this moment, there is a risk of regulatory restriction. It is in a full dynamic stage at the European Commission under this point of view, but we must be stay on the safe side and expect some restriction for the use in flow batteries, not only in flow battery, let's say. As regards the electrodes, even here we have a number of issues. Voltage losses, all kinds of voltage are involved in the electrodes, and so the area-specific resistance that synthesizes the previous. The species dispersion and the kinetics for the electron exploitation, which means how the electrolyte flow through the porous electrode facing an hydraulic drag that results in pressure drop and so in losses. The presence of shunt current, which are an important side effect in this kind of devices. The energy efficiency at high current density, which is also important. If you want to have more compact system, we must go into higher current and maintaining high efficiency, but this is also strongly correlated to the area-specific resistance again. Mass transfer performance, which impact on the pressure drop. And another problem that is important and not totally exploited is the electric contact resistance between the different layers composing the faces of the electrode, particularly toward the bipolar plate, and the cost of the electrode itself. Here again, we can formulate all this issue in terms of key parameters that affect the pore side, the fiber side, the surface area, the hydrophilicity, the presence of some kind of catalyst, the use of nanoparticles, the differential porosity, and so on and so on and so on. I don't go into too much detail. And what are the paths to improve these issues acting on this factor? There are different strategies. Actually, in this case, direct functionalization, the position of electrocatalytic nanomaterials, new carbon fiber, precursor material, and also different materials for the positive and the negative electrode, where different performance are exploited. And again, there is a wide literature proposing solution to go into this direction. Here is a number of this article that I have selected. And following what has been published, we can assume that the area-specific resistance can be reduced by 2/3, and so reducing to 1/3, while the current density at the same time becomes 3 times more higher. Okay, so electrodes. Now we have also improvement achievable on the flow field, which means how the electrolyte are distributed to the electrode inside the cell, sorry, and also how the electrolyte flows inside the wall stack, the stack hydraulics. And there are a number of issues again, which means hydraulic drag, shunt current again, of course, but everywhere where the electrolyte flows, there is this problem. Engraved, which can be made in different way, bipolar plate instead of flat bipolar planes. with large active areas, and which are not easy to produce if the active area of the cell are quite large, as required in the industrial system. This is the meaning. And so the size and the number and the shape, I must add, of the channel itself, the electric contact resistor, again, the other side, of course. Here again, there are a number of factors that impact on these issues. The kind of flow design, flow through or flow by, I already mentioned. The flow paths, the pressure drop, the electrolyte conductivity, differentiated, I must say also, the efficiency, the resilience and durability of the material, the impact of the duration. And here again, there are paths to improve this factor. I don't want to delay on this, reading all these words that are reported here, but you can quickly understand that all of them actually can provide improvement also on this point of view. And here again, we have a vast literature reporting how this suggesting, proposing improvement under this point of view, which can result in quite dramatic reduction, improvement, which means reduction in the losses, both for shunt current and for pressure drops, as you can see here. Then it is not finished. We have also other factors to consider. We can improve the control. The control means performing high-level control means being able to work with the standard state of charge with balanced electrolyte, avoiding hydrogen or oxygen evolution that requires next regeneration processes, which means actually avoiding regeneration processes, minimal hydraulic losses at the same time, maintaining top performance without affecting the electric performance, electrolyte tank mixing to avoid this negative effect inside the tanks. When the tanks are very big, this can be an important effect. Then key factors are the dynamic flow factor, the pump performance, the tank design and control, the efficiency, and so on. And this can be achieved with improved control in the flow battery management system with multivariable flow rate optimized, particularly depending on the state of charge and on the loading condition. Here again, the literature is proposing interesting solution, and the development can be this. We can achieve a wider range of state of charge from 80 to 90%, which means actually is the same as saying that we save 10% of the volume of the electrolyte, and we extend at the same time the durability of the system, as you can see. Then we can act also at manufacturing level. Manufacturing level means that we can reduce the manufacturing cost and the component cost. How? Using large-scale cell component production, going into this direction. If the market expands, more producer can provide membrane, electrode, and so on, and the cost in this condition. So the economics says will go to reduce. But we also can introduce automation and robotization at manufacturing level and other economies of scale. And the results, these are some references that we have used. The result is that the materials and components can reduce by 20 to 30% and the assembly cost by 50%. It means that related to the material cost, assembly can reduce from 10 to 5%. This is the meaning of this figure. And then we have also aspect regarding the market. The market material, the component price, electric price, and vanadium end of life. This is all market. The path is to reduce the material and component while the market goes toward maturity. And vanadium end of life gain a real value as the vanadium recycling chain is activated. Here there are studies on this point, as you can see, from the World Bank. And the result can act in this way. Vanadium price dynamics can reduce. Electricity price dynamics after non-dispatchable renewable energy storage will expand, which means that the price for selling will become more and more high than the cost for buying. The mature vanadium electrolyte market will mean that the end-of-life revenue will be an asset, while it is not now. And appearing in the market of a competing manufacturer for components and for raw material will also involve a reduction of cost and price. If you think, for instance, what was the cost of the early mobile phones and how it reduced dramatically over just few years, you have an idea of the impact that the market can have on the cost of components and materials. And also finance can impact, because as the investment becomes less risky, because the technology consolidated, the discount rate will reduce. Here also there are studies on this aspect, as you can see, and so we can expect that the discount rate that we assume in 10.8% in the computation that I presented, the simulation that I presented, will reduce to the half, and so. And now I go into real evidence of this evolution of the prices, at least for the price of electricity in Italy. This is the evolution above about 20 years, 18 actually, from April 2005 to 10,010, always April, 2015 and 2023. You see what happened. Price was almost enough stable in the beginning, and this tried to expand. And after some fluctuation here, it tried to expand a lot in very recent year, last year actually, and with the very high prices and sometimes during early morning and evening, and very low prices during the sunny hours during the day, when PV systems are in operation. This is the meaning of this. The expansion of the photovoltaic power station put on the grid, in this way on the market, larger and larger amount of energy, and the prices in this condition always reduces. This is a law of market, of course. And this is what will go on continuing the next year, while the penetration of PV and wind in other countries will expand. So we can expect that the perspective price of electricity rise up in few years, 250 when we sell, and reduces to some 70 or about euro for megawatt hour, I mean, when we buy during the sunny hours of the day. And this is, of course, a profitable condition for us, because we buy a low price and sell at high price. We are putting the system on the market. And this impact on our economic performance indicators. One can say, but okay, this is Italy. It is an evidence that we can accept also in other countries, in other regions, or so on. Well, I present you what is happening in California. I was discussing this summer with a guy working on investment in energy in California, and he said to me, oh, in California we are at least 8 years in advance on Europe, and you will experiment what we are doing now in California in 8 years or so. I don't know if it is true, but it's interesting to say, to look at what is happening in California. This is the similar evolution to what I presented to you before over the year. You see, 215, 16, 17, and going down to 222 with the evolution of this is the gigawatt of power put on the grid. And more power put on the grid and more during the times goes like this. And this effect in terms of price, here we have the cost of the, this is the energy demand actually, sorry. This is the energy, the power demand. And as the demand reduces for self-production and so, the prices reduces, as you can see here. So there is a reducing over the year of the lower price when you can buy and an increasing of the higher price when you can sell. And this is not the evidence of a single operator. Is this investigation made by the Energy International Agency, but is also done by other agencies, as you can see here. And what can happen is that the price can reduce dramatically when it is convenient to buy, even to the point to become negative in some moment. And this is reality actually, because you see this is a dynamic evolution of the price of energy in California, produced by the same company that gave this diagram. And you can see that sometime here the price is even negative, which means that if you buy energy in this moment to store in your system, you even are given money to do this. And so the business became extremely profitable. So, and what can we do about the evolution of the price of vanadium? Of course, we have a lot of other chemistry, and we hope that they give excellent result in the coming years. But in the wild, what is doing vanadium? Vanadium is maturing in producing specific solution for electrolyte in flow batteries. The Vanadium Corporation gave this news this spring, as you can see, and at the same time, extremely important deposit of ore containing vanadium have been found in the Scandinavian countries. I mean Norway, Sweden, and also Finland. And you see the report on the press given of this evidence. Massive investment in mineral extraction is needed now, and you see this is exactly vanadium it goes on, which means that as vanadium is put on the market in larger quantity, we can expect that the prices reducing. Interesting, this is also in Europe, and the can impact of the classification as critical raw material for vanadium, but don't go into this factor. We wait the European Commission to take consciousness of this evolution. We only consider how the price can evolve. Okay, now I say, I put all together all the provision that I presented, all the forecasts that I presented based on scientific data and market data, as you can see. And what come out is this. This is the same table of parameters that I presented you before, with the difference that the value that you see in red have been updated according to the forecast that I introduced before. And if I run again my techno-economical model, this is what comes out. This is the unit capital cost that now reduces to 200 respect to 300, which is an improvement, interesting, but you can say not exceptional. But look at the levelized cost of storage. The levelized cost of storage reduced to 8 cents for kilowatt for cycle, which is extremely close to the 5 cents, which is the target of the Department of Energy in the United States, as well as of the European Commission here in Europe. Of course, for a system for long duration, you see, we are here. Long duration is where it is interesting to consider these technologies. And if we go now to look at the net present values, we see what this cost on the left impact. And the fact is this, You see, the diagram is completely green here. It is always profitable at any level because the duration from 2 to 10 hours, stay exactly here. So we can say investor here, you can invest in this technology and you get the profit from this. This is what is expected in a few years, 5 or 4 or 5 years, I say, possibly some more, but in the order of this. And now the question is this, we see all these factors put one after the other. Which benefit gave in reducing so much the costs? And you see the cycle life extension 18%, the improvement in stack power 4%, the value for end of life of the vanadium 18%, and so on. And so on and so on. The dynamic of price is 15%, the discount rate 16%, the concentration, higher concentration of the electrolyte 20%. Altogether, they 74% of cost reduction, which is a very impactful value. It can seem to be fantasy, and in fact, the next question is this. The second big question is after, will they become profitable? Is that science or science fiction? Am I wandering in the heaven, or am I staying on the ground with my feet? And so to answer this question, I will present you two interesting stories, which has nothing to do with batteries. This one. This guy is William Shockley, which in 47 invented the transistor, together with other two guys at Bell Labs, actually. A few years later, they got the Nobel Prize in Physics for the invention because it was becoming a really fruitful fit. We know now, but at the moment it was not clear. And in fact, you see, a couple of years after the Nobel, these two guys, they were very young at the moment. You see older picture here. Jack Kilby, sorry, and Robert Noyce invented the first integrated circuit. Kilby with this one and Noyce this one, actually. And also here, a year later, many years later, a Nobel Prize came, but only for Kilby, which was the first one in 58 in this case. And what this did, this gave the idea to this other guy, which is Gordon Moore, to introduce what is now known as the Moore law. And he published this in a not very, very important magazine in the United States, electronic magazine. It was not Nature, it was not Science, not JAWS, and so on. But it was a forecast for the invention of the integrated circuit. And the forecast is this. He said, in 59, this guy, Robert Noyce, invented the first planar integrated circuit. Now we are in 65, and come on, and we are here. This point in the middle are almost on a line in a semi-logarithmic diagram. Here is linear, here is logarithmic, as you can see. Here we have the number of components that the industry is able to put inside a single integrated circuit. And he said, I think it will go linearly, like this, over some years. And linearly means actually an exponential great growth, of course. And this was, as I say, Gordon Moore, when he was at Fairchild Semiconductor in 65, he actually was working at Shockley together with Noyce some years before. And after this, these two guys together founded Intel, with that to become the giant of integrated circuit for several years. And what happened later? So 75 is here. Here there is 71, some years earlier. Let's see what happened. In 71, Intel, exactly Intel, built the 4004, that was the first chip, the first high density integrated circuit. And this is how this was built inside, more powerful, more reliable, and much smaller than the first electronic computer of just 30 years before. It was the first microprocessor and opened the door to the building of more and more power integrated circuit with a very large scale of integration. These were the guys who had the idea of inventing this. Ted Off, this guy, conceived the circuit, and Federico Fagin invented the way to build the system, and he signed his invention. Federico Fagin is written here, so nobody can argue on who was the real inventor of the physics system. And now, what happened to this first microprocessor? Where did it was? It is here. And this is what happened over the year. The Moore law maintained true for over 40 years. And I may say it is maintaining true for 70 years, but it's enough to say what is happening here. So from the starting 2,300 transistor in the same circuit of Federico Fagin, now 10, 12 years ago, 13 years ago, the number of transistors increased by 1 million times. It is amazing, really amazing. And nobody in this moment could imagine what could happen in the future. But technology went in this direction, and this improvement were possible. This is the miracle of information communication technology and also or artificial intelligence now, we can say. And this is not science fiction, but things that no book of science fiction in that year had imagined that internet could happen. So the technology is amazing sometimes. It's able to achieve incredible results if the proper effort and intelligence is put into its development. Okay, you can say, this is microelectronics. We are not working on microelectronics. What are you telling us? This is not our work. So I tell you another story, which regards instead electrochemistry. The first lithium-ion cells was commercialized by Sony, you see, in 91. And if you look at the cost at the time, the specific cost, it was 7,500 US dollar for kilowatt hour. And the energy density was in the order of 100 watt hour for kilogram. Now, what happened over the year? What happened over the year is shown here. This is in function of the cumulative capacity of produced lithium-ion cells. You see that the prices reduces dramatically over the year. Here it stops at 2016, but it's clearly what happened. The price from the original 7,500 dropped to around 200. This is a different way to see the same things in function of the years, and again the same value in about 218. And what did the power density, the energy density, sorry, in the Y? This is what happened. From the initial 100, it rose up to around 600 now. These are possibly not immediately on the market, but they will become quite soon. So this was what happened, and what was the result of this? And the result of this is that not the guy on the left, of course, the guy on the right and the other two won the Nobel Prize in Physics 5 years ago. Okay, so concluding, these miracles are possible. They need investment, research, and intelligence to put in the right direction the main effort. So substantial flow battery techno-economic improvements are likely in the next years. Dramatic impacting of the key performance indicator, as I show with my model, in competitiveness and in profitability. All consider a techno-economic factor that I presented to you impact, but the major contribution can come from, so they are more strategic, the electrolyte performance cost, the advanced control made by the flow battery management system to exploit a wider state of charge and avoiding hydrogen evolution, so as to avoid any regeneration need. extended cycle life and calendar life, which means resilience of exposed material, membranes, electrode, gasket, and so on. Electricity price dynamics after the renewable energy sources expansion, as I showed. Market maturity, which will be very important as well. And the end of life value for vanadium. But what is more important above all is the strategically addressing the technological solution to meet the market needs is crucial, which is we must look at the first slide that I presented you, which are the services that will be required by the market and by the general economic evolution, and to go in this direction. Okay, and with this, my talk is concluded. Thank you for your attention, and I'm here waiting for comments.